All right, welcome back, everybody. It's time for a little late night lecture. Who knows when you're watching it, but I'm recording it at like 8:13 p.m. on Wednesday night. So just make sure that you've watched this by the time that we have class on Friday. Okay, so where were we? Well, we had just discussed the differences between what we're calling small numbers, large numbers, and very large numbers. Now, I would just like to briefly review some properties of logarithms and exponents. So let's remind ourselves what the definition of the logarithm, the natural logarithm specifically is. So we define the natural logarithm function such that when you exponentiate it, and it's got a function of x in its argument, that it just spits out x back. Or we could also write this, instead of using the ln notation here, we could write log and then specify base e of x equals x. Okay, so that's just how it's defined. Let's look at how it looks on a plot. So this is ln of x, this is x. So if we plug in 0 here, so if we plug in 0 to be x, this is going to shoot off down to minus infinity. And then log of 1 is going to be 0, because basically the log function is just saying to what exponent do you need to take e to get whatever the argument is? Well, the exponent that you need to take it to get 1 would just be 0, so that puts us right here. And then if you were to keep on going on and on with this, putting in other numbers and seeing what exponent you need to put e to get that argument, you would see something that looks approximately like this. Okay, so that is log of 1, and it is at 0. Okay, so that's roughly what the plot looks like, and it asymptotes out here to minus infinity. Now let's prove some other properties of moving logs around. So e to the ln of x, we'll just rewrite our definition, equals x. Now, if we take e to the ln of x, multiply that by e to the ln of y, then by our definition right here, this should be x times y, right? Well, we can also write this right here, the product of two exponents, as e to the ln of x plus ln of y. And so we've already said that that should be x plus y, or x times y. So now if we take e to the ln of x times y, that should also be x times y, just by this definition right here. If we put in xy instead of x on this side, we should just see whatever's in the argument. So we put xy here, we should see xy on the right-hand side. So if we take these two and put them together, so this is x times y, this is x times y, then it must be the case that e to the ln of x times y is equal to e to the ln of x plus ln of y. And now we can just take the logarithm of both sides, drop the exponents, and we have our first nice property, which is that adding the logarithms is the same as multiplying the arguments. Okay, so that's an important result. Oh, by the way, I think this is problem 2.12 out of Schroeder, just in case you wanted to know. Okay, now let's do something else. Let's take the derivative of e to the ln of x. By definition, this is also the derivative of x, which is 1. Okay. Well, now if we take e to the ln of x times d over dx of ln of x, that should equal 1. But then we can rearrange this. We can write it as e to the minus ln of x equals d over dx of ln of x, which is just 1 over x. So we've now shown what the derivative of log of x is, and that's just 1 over x. And likewise, if you integrated the right-hand side, then it would give you log of x. So integral of 1 over x is log. You probably already knew that. What else do we want to show here? Well, running out of space down here, so I'm just going to put part D up here. All right, we've already said that obviously ln of 1 is going to be 0. Now what we want to do is we want to expand ln of 1 plus x for small x and see if that can give us some kind of approximation. That's nice. Well, what can we do? We just take ln 1 plus x and we write the series expansion about the value x equals 0. So the first value will obviously just be the function evaluated at the small point that we're sitting at, so x equals 0. And then the next term in the expansion is going to be the derivative of that function, so d over dx of ln of 1 plus x. And then we are supposed to evaluate that at x equals 0 and multiply by x, not y, x. And then it would go on and on. You would get higher order stuff. We're taking x to be infinitesimally small at this point in time, so you can safely set all the higher order stuff to 0. And so this is your approximate expansion. So we know that this term is just going to be 0, right? Because it's just ln of 1. And let's see, this term right here, we said that the derivative of ln of x down here is 1 plus x. So then it must be that derivative of 1 plus x is just 1 over 1 plus x. Evaluate that at x equals 0, multiply by x. And what do you have? You just have x. So we've shown that ln of 1 plus x is approximately just x for small x. Okie doke. So this will all be useful moving forward. Okay, now we're going to introduce what we call Stirling's approximation. And if you'd like to see a full derivation of this formula I'm about to present, if you have access to the book, probably you all know how to get access to just about every textbook. If you don't, just let me know. You can look at this textbook. It's called Patria and Beal. It's the statistical mechanics textbook, but it's a graduate level textbook. So I'd only recommend looking at this if you're really, really curious. But the name of the textbook is, well, yeah, what is the name? It's just called, I've got it over here. It's just called Statistical Mechanics, and it's by Patria and Beal. You can look at these pages if you want to see the exact derivation of this. But for now, we're just going to take it as a fact that Stirling's approximation is an approximation that you can use for the factorial. When n is really, really large, it becomes more and more accurate. Okay, so n factorial is going to be approximated as n to the n times e to the minus n. And then you've also got this weird factor of 2 pi times n. So this is valid for n much, much greater than 1. Okay? And if you want to prove this to yourself, just go ahead and plot these two things versus each other and increase n and see how the approximation gets better, see how it gets bad for really small n. Maybe I'll make a little Mathematica plot of that and show it at the next class or something. But we can also convince ourselves that this is likely the case, even if we can't rigorously define it or rigorously derive it at this point in time. So we know that factorial just means that we're going to take n, multiply it by n minus 1, multiply that by n minus 2, and then on and on and on until we get to the end. right? So if we were to approximate it, let's say approximate by e to the n, or sorry, no, not e to the n to the n. Well, this is going to be obviously a big overestimate, right? Because you just keep multiplying by factors of n. But here, every single factor is getting smaller and smaller by 1. So it actually turns out that each factor here should be smaller than the previous one by a factor of e to the minus n. So, well, yeah, I guess what I'm saying is that, so obviously this is a gross overestimation. So maybe you can convince yourself that throwing on this e to the minus n will bring this overestimation closer in line with what n factorial looks like, because the e to the n in front of every single one of these terms will lower it by just a little bit, proportional to how far out in the expansion you're getting, right? So hopefully that gives a little bit of insight as to why you can actually use this approximation. But obviously we didn't explain anything to do with the square root of 2 pi n. Don't worry about it. If you do want to see a rigorous definition, seek out Pythagorean Beal, or probably just Google it and you can find a nice derivation somewhere. But this is going to be an important formula for us, and we are going to use it momentarily. Okay, so let's now look at the multiplicity of a large Einstein solid. So hint, the word large here is going to allow us to invoke Stirling's approximation. So multiplicity of large. Okay, so we're going to consider, let's say we've got n oscillators. So n is the number of oscillators. And let's say we have q units of energy. Okay, so we had previously shown the result for the multiplicity function. So we had big omega of n and q is equal to q plus n minus 1, choose q. And that this binomial coefficient can just be written in terms of the factorial, like so. Q factorial times n minus 1 factorial. So what we're going to show now is that we can apply a bunch of different approximations using the fact that we are considering n to be very, very big. Let's actually write that explicitly. Let's assume n is much, much greater than 1. And we're going to find a nicer way to write this multiplicity function and then eventually be able to talk about what the peak actually looks like, because we've simplified it in this way. Okay, so the first and easiest approximation that we can use is that if n is really, really large, then we can just neglect this 1 right here, right? It's just not going to contribute anything because n's a huge number, 1's just a small number, so we can just forget about it. So that's our first approximation. So approximately q plus n factorial over q factorial times n factorial. Okay, now we're going to apply Stirling's approximation. Before we do that, let's get on another page. So let's rewrite that. So we have sigma of n and q. That is q plus n factorial all over q factorial n factorial. Okay, so now let's apply Stirling's formula. So before we do that, we want to take the natural log. So let's do that. Natural log of omega of n q It's just the natural log of that expression we have right there. So that is q plus n factorial, q factorial, n factorial. Okay, now before we actually use Stirling's approximation, we're going to break this up just using the properties of the log. So we have this on top and this on bottom. We can just use the fact that adding or multiplying and dividing inside of the argument is the same as adding and subtracting outside of the argument. So we'll break this up. So we can write it as ln of, let's use a bracket here, q plus n factorial, then minus, because these are in the denominator, ln of q factorial minus ln of n factorial. Okay, so far so good. Now is where we actually use Stirling's approximation. Maybe I shouldn't have written it up there before. Let's get rid of that. Now we'll write Stirling's. Okay, so yeah, let's use Stirling's approximation, which we had over here before, just to rewrite these expressions. And the way we're going to use Stirling's approximation here is we're not going to include this factor right here, the square root of 2 pi n. That's going to effectively just go away entirely. Oops, it looks like I forgot to actually finish writing out the form of Stirling's approximation, the form that we're going to want here. So what we're going to want for what we're doing right now is the natural log expression of it. So I'll just do it right here. So we're going to neglect this square root 2 pi n term because these terms are just going to be so much larger than it. So something that's of order n to the exponent of 1/2 is going to be really, really, really small and insignificant compared to this term right here specifically. It's not going to change this by very much. So the first thing we're going to do is we're going to rewrite this as n factorial is approximately n to the n e to the minus n for all of our purposes. And then since we're going to be doing a lot of expressions working with the natural log of n factorial, we're going to write Stirling's approximation in this natural log form. So let's take the natural log of the right-hand side, e to the minus n, and then use properties of the natural log to break this up. So we can write this as ln of n to the n, and then plus ln of e to the minus n. And again, using some properties of the log, we can pull down the exponent outside here. So this is going to be n ln of n. And then ln of e to the n is just going to be minus n. Okay, so this is actually the form that we're going to want here. And I'll write it more succinctly, equals that. Okay, so now let's go to the next page. Let's rewrite that just to make sure it's right in front of our eyes. So we have that ln of n factorial equals n ln of n minus n. Okay, so now we should be in a good position to rewrite this in terms of Stirling's approximation. So if I'm correct, this should become q plus n times ln of q plus n minus q plus n. That's what this first term turns into. Okay, now let's apply it to the next term. So this will be, well, we'll put a plus here, even though it's a minus, we'll flip the signs around. So this will be minus q, ln of q. So this is minus, since we had a minus sign out here and there's no minus sign up here. But since this term is negative and this term is negative, it cancels out and we get plus q. And then doing the same thing for the next term, we'll have minus n ln of n plus n. Okay, cool. Now let's regroup some stuff a little bit. So no approximation here, so we're just going to write a normal equals. So let's rewrite this just a little bit. Move some terms around, regroup them, and then we'll be able to cancel something out. Ln of n minus q plus n, then plus q plus n. So notice that we have a minus q plus n here, and we have a plus q and plus n here. So those two terms, they cancel out with each other. Cool. One more thing that we need to do is we're going to take this term and we're going to expand it, again, assuming that q is much, much greater than n. So we're going to use the approximation that we proved before, which is that ln of 1 plus x is roughly x. So how can we get that out of here? Well, this will be a nifty little trick that you should keep in your pocket for a rainy day. So we can rewrite this, just pull out a factor of q, right? This is 1 plus n over q. And now let's rewrite this again, just using property of the log. So this will be ln of q plus ln of 1 plus n over q. Hello, cat. You can't be up here while I'm writing. Hey, get off. Sorry, I've got a cat trying to invade writing space right now. Okay, hold up. Sorry for any cat interruption. Oh, where was I? Okay, so let's see. Yes, so now we're going to make the additional assumption that Q is much, much greater than N. This is a so-called high temperature regime where the number of units of energy is much, much greater than the number of oscillators that we have. So in that case, then just by the result that we had before for when this is just x, if x is really small, in this case, this number will be very small, then log of 1 plus whatever that number is just that number back. So we can approximate this in the high temperature regime as being ln of q plus n over q. All right. So now taking this result and plugging it back in. Oh my, we just have a lot of cat noises going on right now. This is what a day in the life of me is like. Oh, okay. All right, let's put this back in. Q plus n times ln of q plus n over q, just taking what we had found right here and plugging it back in. And then we also had minus q ln of q minus n ln of n. All right, so now we can just distribute this q plus n onto these guys right here. And so we'll have a q ln q plus n ln q plus q times n over q plus n squared over q minus q ln q minus n ln n. All right, so we see that this term cancels with this term, and that these two terms are also the same. So they will also, oh, sorry, no, they are not the same. Do not cancel those terms. ln of n. Now, what we can do with these two terms right here is we can combine them since they have the same factor of n out in front. So we'll do that. So we can rewrite those underlined terms as n ln of q over n. And then we've got an n plus n squared over q. Okay, but keep in mind that we assumed up here that we have the high temp assumption, which is that q is much, much greater than n. So this term is negligible since you have q down here. So forget about it. All right, so move into the next page. we have that in all, ln of omega is equal to n times the natural log of q over n plus n. Now we can just exponentiate to get back to the actual multiplicity rather than just the log of the multiplicity. Although we'll see that the log of multiplicity is actually what we're going to care about because this is directly related to entropy. Let's just humor ourselves for the moment. So e to the ln of omega is equal to omega of n and q, which we've just shown is approximately e to the n ln of q over n plus n. And we can just rewrite this piece right here because it's e to the ln as q over n to the n. And then we just have another factor of e to the n, so times e to the n. So all in all, we can write this as e times q over n to the n. All right, so for q much, much greater than n, and n much, much greater than 1, we have this. That is omega of n q. So it's approximately equal to that. All right. So now what we want to do is we want to show how sharply peaked this multiplicity function is. So the whole reason that we did all this was just so that we could actually understand how the peaking works. Okay, so now what we'll do is rather than just considering a single solid, which is what we were doing here, we'll consider two of them. So we have two Einstein solids with multiplicity functions that look like this. If we want to look at the total multiplicity of the system, remember that you take the multiplicity for system A times the multiplicity for system B. And that gives you the total for the entire system. Not the entire sum over all the macro states in general. It's just going to be the total multiplicity for the system for that macro state. Okay, so let's calculate what this is in terms of this approximated multiplicity function here. So we'll write our total multiplicity like this, approximate it as EQA. QA just corresponds to the number of energy units in oscillator A. And then QB is just the number of energy units in oscillator B. And don't confuse yourself when you walk away from this for a few days and come back and see an E here and think that it has anything to do with electric charge or something like that. It's just it's the natural number E. So rewriting this, En to N, and we can write QA and QB together because they're buddies to the N. But rather than writing it in terms of QA and QB, we can just note that QA and QB are constrained to run together because QB is going to be N minus QA, right? So, yeah, that's all. So if you look in Schroeder, he walks through in more detail one of the examples that we kind of talked about before, and he shows numerically how the multiplicity function peaks. It reaches its maximum value when the energy units are distributed equally across either system. So this is just something we'll take as an experimental fact for the moment. It maxes out at QA equals Q over 2. And so at this value, so the multiplicity, the maximum at this point, we can just evaluate at QA equals Q over 2, and also substitute in N minus QA for QB right here. So this just becomes E over N to the 2N times QA over 2 to the 2n. So that is the highest the multiplicity gets for the sum system, not just one or the other. So now what we want to do is we want to see what the graph of this multiplicity function looks like at that peak. So how can we do that? Well, we can use this following trick. So we're going to just consider perturbations around it. So we'll consider QA, rewrite that as Q over 2, which is the max we know. And we'll just add some small number x to it. Take QB, write it as what its maximum value is, Q over 2, minus some little perturbation x. And so we're going to use this to look at the x much less than Q region. Or sorry, we'll use x to be something really, really small to look at the really peaked region. So let's put this into omega. So omega now looks like the following. E over n to the 2n times q over 2 plus x times q over 2 minus x to the n. Simplifying this further, okay. Now, let's consider the natural log of this. So let's consider the natural log of q over 2 minus x squared, all of that to the n. So we're just looking at the natural log of this term right now. Well, the n can be pulled out because this is a natural logarithm, so it'll just be n ln of q over 2 minus x squared. Should really write brackets around here to denote that the natural log is of this entire argument right here, and that the exponent n is not sitting outside of the log. So now let's rewrite this. We'll just pull out q over 2 squared, and we can rewrite this as 1 minus 2x over q squared. So we're just rewriting this interior right here in terms of that. Now, do a little bit more mathematical massaging. Ln of q over 2 squared plus ln of 1 minus 2x over q squared, just again using the property of the multiplication inside the argument of the log. Oh, I did something bad here, didn't I? Yes, I did. Okay, so this is right. This is right. This is not right. There's not a natural log there. It's a shame nobody can shout at me when I'm recording this remotely without anybody's input. Okay. Now, we can approximate this as n times the natural log of q over 2 squared minus 2x over q squared. Okay, so in order to get here, we're just using the fact that this x is really, really small compared to q. So that's an implicit assumption up here that I said out loud but didn't write. So x is much, much less than q. So this term, as we were mentioning before, it's of the form 1 plus x, but now it's 1 minus this quantity. So it just becomes minus quantity 2x over q squared. Okay. Now, let's exponentiate this. There's a lot of steps, so make sure you're following along. All right. right? So just using the property of the natural log being exponentiated, this becomes q over 2 minus x squared to the n. And this is approximately e to the n times ln of q over 2 squared minus 2x over q squared. Okay. Now, writing out the multiplicity all over again, we have e over n to the 2n, e to the n, and then times this quantity that we just figured out, minus 2x over q squared. And we can just identify this fact out in front. Well, hold up. Yeah, so we'll identify this whole term right here as just being what omega max is. So that's the maximum value. Whenever x is 0, that's just the maximum value. And then times this nice looking function, which you have likely seen before. So at this point, I would ask the class if anybody knows what this form of function is called, but there's nobody to answer. So I'll just say it's called a Gaussian. And so if you are familiar with the form of a Gaussian, then you'd be able to identify the standard deviation squared as just being the quantity related to q squared over 4 times n, which tells you that the standard deviation for this Gaussian recovers the well-known fact that you might know, that for like Gaussian statistical processes, the error goes like 1 over square root of n. Maybe you don't know that, but that's something that I always remember. So yeah, this is just telling us that as n gets really, really large, the standard deviation, so standard deviation is basically just telling you the spread from this value, the peaked value, that as n gets really, really large, this gets really, really, really small. So if n is like of the order 10 to the 23, this becomes extremely, extremely peaked. So if we're only looking at like n of order like 1 or 2, so like let's say n is like order 1 or something like that, then this looks something like the following. So it looks like I was showing in my notebook, my Mathematica notebook the other day. But then you can see, so like this is, let's say that's like 1 sigma. So now as n turns into like something that's what we call a large number, then you get something that looks like this. Looks bad. It doesn't actually double on itself. And then maybe if you have n to be a very, very large number, so like even this isn't really that big. Like an Avogadro's number of oscillators isn't really a realistic thing. So let's say we're talking about something that is 10 to the 10 to the 23. Well, now you can't even believe how peaked this is. For all intents and purposes, it just looks like a single line going straight up at this maximum value right here. So because we can tell that it's a Gaussian, we can identify what the spread is in terms of the number of oscillators are in here. And therefore we can see why it becomes so peaked as the number of oscillators grows and grows and grows. Okay, so I hope that was helpful. That's all we're going to cover right now, and maybe I'll upload another asynchronous lecture sometime tomorrow, which is Thursday. All right, thanks.